So now let's get back over here. I told you about this specific topic. S equals r theta is the formula to get the arc length. And we just discussed that this orange length, it looks biggest among the three different colors A, B, and C. Each of these A, B, and C are representing three different satellites. And you told me that orange satellite, when it traveled 2 radians of an angle around the Earth, has covered the maximum distance. It's clearly visible over here. But how will I support that claim mathematically? This formula is telling me the arc length S is equal to R times theta. So theta is fixed. For all three, theta is 2 radians, right? For each of these, theta is 2 radians. Theta equals 2 radians. So theta is not changing. What changes? The arc length is only the radius. Here, let's say this is the O. So from O to C, OC is the biggest distance, the biggest radius. So that satellite will definitely travel for the max to cover this distance, right? Arc length depends upon the radius and the angle of rotation. If radius is bigger, arc length will be bigger. Now let me tell you easy thing, easy hack. You have three measures over here, the arc length, the radius, and the theta. If you are given any two of those, you can find out the third. So I can give you many different variations of a question. I can ask you, what's the arc length? If radius is this, theta is this. I can also ask you, what's the radius? By giving you the arc length and the theta. So you can just manipulate, change a little bit this formula, and that will give you the other things. If I will change and I have an arc length and a theta, I can find out using this formula the radius. Agree? What did I do? I simply divided both sides with a theta and then gave me the formula for the radius. Radius is equal to arc length divided by theta. Or the third variation, we can also find the theta by arc length divided by radius. Any two measures, if given, can help you to find out the third measure. Make sense? Now I'm going to relate this to many other things in a few minutes. If you have already taken the notes for this part, let me tell you one thing. If you read this paragraph, it was telling you that a group of more than 20 satellites make up the Global Positioning System, GPS. Have you ever used a GPS system? Yes. When do you use it? While driving? Which app or application do you use during that? Maps. Google Maps or Maps are giving you the location, exact pinpointed location of any place that you want to go. How does that work? These 20 satellites are helping you to figure out a pinpointed location, and then they have done a lot of other work also to draw those maps, bring in all the roads which are actually existing on the Earth. But if these 20 satellites are not coordinating with each other, the maps will stop working. You can Google it later also, but let me tell you one thing. These 20 satellites are on a static position above somewhere in the atmosphere, like even out of the atmosphere around the Earth. They are on the static position that they are exactly rotating around the Earth with the speed of the Earth rotation. You do know that Earth rotates, right? Yeah. And the rotation of Earth is so much synchronized, the satellites are exactly moving at the same pace somehow that they will always stay exactly on top of one static point. So their speed is definitely greater than the speed of the Earth's rotation. Then the GPS will fail and you will not be able to go home. You will not be able to travel from home to somewhere where you want to go. Has that ever happened? No. Maybe accidents always happen. I'm not aware of that. But since the Maps are working even up to a few meters, accuracy is there. So it has not happened like recently. I don't know what. We can Google it if it has ever happened or not. Now let me bring in one thing here. Because I was just talking to you about the satellite's rotation must have more speed than the Earth's rotation, because let's say if this A, the blue circle, is representing the Earth's surface, and Earth is rotating around this angle with the rotation 2 radians, this point from here to here is telling us the rotation of Earth. Let's say Earth took something like 8 hours from here to here, and the same time the satellite at the point C took to rotate with the same 2 radians from here to here. This speed must be greater, right? Because the satellite is covering more distance during that same time with the Earth rotation. Does that make sense? It will make a little bit more sense. Let me bring now another example over here. Have you ever Googled the 3D model of Earth?
Oh yeah.
Ever done that?
When they changed the name to Gospel of America, it's check the.
Okay, let me do it now. What I'm gonna do, I will bring the 3D model of Earth. That's a 3D model, right? It's rotating, right? Where are you on this model?
Just go to the real one.
This is a real model. It's by NASA. Where are you at this time? North America?
Right there.
You should be somewhere.
Right to the right.
Keep going. Thank you. Over here. We are. I don't like it. Like it's not a very good response. But you're somewhere over here, right? This is Florida. This thing. Oh, I can zoom in also. Very good. Very good. So this is Florida. This tip. And somewhere over here, you are sitting over here, right? Now let me do this. If I'm rotating like that, the Earth, this whole circle, like this whole rotation, how long does that take? Oh my God. What's this on top? What's this on top? What do you think? This is North Pole, right? This is North Pole. And if I will go to the other side, let's get that back. I know that I can move these points also. Could we do that? It's not letting me do this. This is Arctic. No, Australia is on the south side. Australia is on the south side. This is on the south side. This is north.
Wait, that's not. Oh, it's the north side.
Arctic Ocean. Yeah, this is the North Pole. The South Pole is down there. Now, what I was trying to bring in, I know it's funny, and I was initially bringing it in here. You can do it yourself also. Pull up 3D model whenever you're home later and try to rotate. My point here is, if Earth is rotating like that, kind of a ball, right? Let's say if you're sitting over here, Earth is rotating. You know how much is the speed of Earth's rotation?
20 miles per hour.
Oh no, not at all. Not at all. Slower. The rotation for the Earth's speed is way more than that. The speed of the rotation is, I think, somewhere around 1,000 mile an hour.
Is that
1,000 mile an hour. Like if you can somehow escape the gravity and stay over here something like 100 feet above, and the Earth will rotate below you, and 1 hour something you can land at Miami. It's possible. Miami somewhere in Florida and somewhere, because Earth's rotation is really fast. 1,000. This rotation is really fast. 1,000 miles plus. You can Google it also later. My point, if somebody is sitting over here at the equator, Michael, Jamaica, if you're sitting somewhere over here at the equator, and I'm telling you, let's assume the rotation speed is 1,000 miles per hour, will that speed be exactly same over here also? Or no? No. it will be less. It will be less than definitely here. Does it make sense? No?
Yes.
Does it make sense?
Yes.
I can tell you with the same thing with this example also. I have this example here. You see this cup? You see this cup?
Yes.
Look at this cup. Here. If I'm rotating it, let's say this cup rotates in 2 seconds. This cup rotates in 2 seconds. Which edge will cover more distance? This one or this one?
The small,
Which edge will cover more distance? This edge or this edge? The top one.
yeah.
More distance because it has more of the circumference, right? In 2 seconds, this is covering more distance. So if in rotation of 2 seconds, we do know that both have rotated for the same time and it covered the more distance, that means this has greater speed, which tells me if we have a smaller radius, the speed of rotation will be smaller. Does that make sense? If the time consumed for the rotation is same, the greater radius will have a greater speed and the smaller radius will have a smaller speed. So this tells us one more thing, that if I'm looking at the orange satellite and they are taking the same time also to cover this distance, then obviously orange satellite has more speed than the green satellite. And same applies to the blue one also. Keep these hints in mind, watch this video again yourself and try to grasp these things that I'm saying. Okay? Why? Because that will be useful for you to respond to the next questions. And what are the next questions? Let's go to that now. Which satellite do you think traveled the farthest distance? You have already responded to that, right? C. So your answer is C. Clearly you said that, but you need to explain it also. Now we have discussed enough to let you respond to the question. Which satellite do you think traveled the farthest distance? Yes, that's a question, but you will not just respond with a C. You need to explain it also. Why will it travel the farthest distance? In your words. You will watch it again. Then question number 2. Which satellite do you think traveled the largest fraction of its orbit? You have this worksheet with you, right? Read the question again over there, and I will bring in the picture again. Question number 2. Let's look at that again. Let's read the question again. One more time. It's saying, which satellite do you think traveled the largest fraction? Don't miss the specific word. This is saying largest fraction of its full orbit. And how do you know? What's the basis? How will you know that? To answer this question, you will again have to look at this picture. What did we mean? We mean if I'm trying to look at the complete orbit of the satellite C, that's the complete orbit, right? Do we agree with that? Do we agree with that? This is a complete orbit. So with this rotation of 2 radians, how will I find out the fraction that this satellite C traveled from this point up till this point? To find out that fraction, what will I do? Let's say if the complete orbit is whole semicircle, which is 2 pi r, what is the length that starts from the point this one, the original location of the satellite C, up till the point over here, which is 2 pi. This arc length of S, we will divide that with the complete circular rotation, which is 2 pi r. So I will find out that fraction by S, divided by C, where C stands for the circumference. Make sense? That's the fraction. That is the fraction of rotation. Fraction, the one that we are talking about. So which fraction will be greatest? What do you think? The fraction for the angle C will be greater, B or A? Which will be the largest fraction?
Wait, is there a fraction of what?
Which fraction
No.
of the arc with its complete orbit will be greater?
It's overseas, the fraction of what?
I responded to your question. I will say it again.
No.
Try to listen to that. You're asking me, what do I mean by fraction? What fraction am I mentioning here, right?
No, I just
Okay.
want you to say what you just said. Like, what is fraction of what?
Yes, I said the same thing. I will say it again. Let me show you first. Here. It's saying fraction of its orbit, full orbit. Fraction of what? Fraction of the traveling of satellite. So satellite is traveling. Satellite is traveling from the starting point up to 2 radians. That draws an arc length. What is the fraction of that arc length with the full orbit?
Oh, it's the fraction of what?
So that thing I'm bringing in over here. The initial position is over here with the C. If I'm looking at the C, initial position for the B is also here. Initial position for the A is also here. And then all of these are traveling for how many angles? 2 radians, right? So we every single time are getting an orange arc length. We're getting a green arc length, and we're getting a blue arc length. What is the fraction for each of these arc lengths with their complete orbit? So when I will try to find out the complete orbit for the blue arc, I will find out that with the complete orbit of the blue satellite. So in the numerator, I will put this dark blue length, and in the denominator, I will put this complete circular length, which is the orbit length or the circumference of the satellite A. But the formula will remain the same.
So fraction is.
The full orbit is going to be in the denominator every single time. Now, let me explain it a little bit with the formula and you will know about that. What is the formula for the circumference? 2 pi r, right? And what is the formula for the arc length? I gave you that formula over here, r times theta. R times theta, right? This fraction will always remain the same. And what's that fraction? That's going to be the r. Definitely we can consider that r divided by r is going to be 1. So what are we left with? We are left with over here theta by 2 pi. Will that fraction be different for blue, orange, and green satellites, or will it remain same?
Wait, no, the formula?
This is the fraction. Let's say this is the fraction that we are talking about after simplification. Did you notice that radius has already been cancelled? The radius is gone. So it doesn't matter whatever is the radius, the fraction will remain the same. I know it's difficult to understand. I know it. And just because of that, note down these formulas and I will explain it to you with an example. Okay? Where is the example? Here. So I'm bringing in the example here now. We can respond to this question. If it's not making sense at this time, let's do it with an example. Here is a table that will help you to understand the same thing. What I'm going to do here, I will give you the values myself. Let's consider the satellite A is at a distance of something like 160, giving an example, let's consider that the satellite A is a distance of 160 miles from Earth. The satellite B is at a distance of 170 miles from the Earth. And then I'm giving you another radius, which is the satellite C's distance from the Earth, and I'm giving you that as 180. What did I give you? Every single time, these are the radius, so I will put an R over here. R stands for the radius. For each of these, try to find out the complete orbit, which is the circumference. What is the formula for the circumference? The formula is 2 pi r. 2 pi r. And for each of these, I have given you the r. So you will simply use the formula to find out the length over here. Like for the first one, what will you do? You will do 2 times pi times 160. That's how you will find out the radius, like the circumference here, whatever is the result, put it over here. That's your circumference of the orbit for the satellite A. Then you will need to find out the arc length, and the formula that I gave you for the arc length is R times theta. Do we have theta here? For the example that we were just looking at a little bit ago, the theta is equal to 2 radians. 2. So theta is 2. Theta is 2. 2 radians. How will you find out the fraction? The fraction will be S over C. S stands for the arc length and the C stands for the orbit. Let me name this as C and let me name this as S. That means whatever is the result here, you will divide that arc length, you will divide this distance S with this C, and that's what you're gonna put over here. And that will give you the fraction every single time. And I can definitely tell you what will be the angle in degrees, because we are looking at the two times radians, and each of the radians is 57.3, almost rounded. So this is going to be 114.6 degrees. That answer I gave you. The rest of the stuff, calculate yourself, and then you're done.